Okay, in section 8.2, we're going to be talking about estimating a population proportion. So P and P hat. So this activity that's at the beginning of chapter 8, it basically says that if I had a container full of different colored beads, and our goal is to estimate the proportion of red beads in the containers. We could go through all of this, but we're going to look at the example they have in the book. So picture a big bin with a bunch of different colored beads, and what we're looking for is what's the actual proportion of red beads that are in the container. So suppose one simple random sample of beads resulted in 107 red beads and 144 beads of another color. The point estimate for the unknown proportion P of red beads in the population would be P hat is equal to 107 were red out of a total of 251 that were withdrawn from the container. So our P hat is estimated to be our P hat is 0.426. Remember, that's the statistics. So how can we use this information to find a confidence interval for P, the population proportion? So there's a couple rules that we have to follow. If the sample size is large enough that both NP and N times Q are at least 10, the sampling distribution for P hat is approximately normal. The mean of the sampling distribution, P hat, should be equal to P. And the standard deviation of the sampling distribution from P hat, you should know from last chapter, is the square root of P times Q over N. So again, remember, we're kind of going back and using what we learned in chapter 7 to do all of this. In reality, we don't know the actual value of P. If we did, we wouldn't need to construct a confidence interval for it. In large samples, P hat will be close to P. So we replace P with P hat when we're checking for the normal conditions. So before we can construct a confidence interval for P, we have to check some important conditions. First, it has to be a random sample. So it has to be a well-designed random sample or randomized experiment. It also has to pass the 10% rule, because if we sample without replacement, which is often what happens, especially when you're doing surveys and things, the number of our sample size has to be less than or equal to 10% of the total population size. That's nothing new. And for large counts, since we don't know P, we have to check N times P hat and N times Q hat and make sure they're at least 10. So here we go. We have this problem. There's some missing information. Let me find it. We're supposed to check that the conditions for constructing a confidence interval for P are met. So in this problem, it says Mrs. Quinn's class wants to construct a confidence interval for the proportion P of pennies that are more than 10 years old in their collection. Their sample had 57 pennies that were more than 10 years old and 45 pennies that were almost 10 years old, or at most 10 years old. We are not given some information here that the book assumes we know, and I'm not sure how they were supposed to assume that. But one of the things that we need to know is that Mrs. Quinn had 2,000 pennies in her collection. So that's our population size. So we're missing that info, and I think that is it. So we have to check that the condition for constructing a confidence interval for P are met. So the first thing we have to check is, do we have a random sample? And yes, because what we did is they took a sample, they took their pennies, and they just did a simple random sample and chose N equals 107 pennies from the collection. The 10% rule has to apply, and since our N for our sample was 107, that's less than or equal to 10% or 1/10 of 2,000 pennies. So we're good there. The 10% rule applies. And then we have to also check large counts. Well, for large counts, it's normally n times p, but because we don't know p, we need to check n times p hat and n times q hat, and that has to be greater than 10. Well, what is our p hat? Our sample, remember, p hat is our sample statistic. Our p hat is going to be, we withdrew 57 pennies that were more than 10 years old out of 107 times that we chose. So that's our p hat. So we have to take n times p. 107 times 57 over 107, which is equal to 57. And that's greater than 10, so we're good. N times q is going to be 107 times q hat, 45 out of 107, which is 45, which is also greater than or equal to 10. So all of the conditions for constructing a confidence interval for p have been met. Okay, so now we want to take this information and we want to try to actually come up with our confidence interval for p. We can use the general formula that we talked about in section 8.1 to construct a confidence interval for an unknown population proportion p. We take our statistic that we know, p hat, and we add and subtract the critical value times the standard deviation of the statistic. So, you probably say, where are we getting all of this information? The sample proportion p hat is the statistic that we use to estimate p. When the independent condition is met, the standard deviation is the square root of p times q divided by n. But since we have p hat and we don't know p, we use what's called the standard error. So we use the square root of p hat times q hat divided by n. We're using our p hat to estimate p. So this is called the error, when the standard error. When the standard deviation of a statistic is estimated from data, the result is called the standard error of the statistic. So, how do we find the critical value for our confidence interval? If the large counts condition is met, we can use a normal curve. To find a level C confidence interval, we need to catch the central area C under the standard normal curve. So in this example, if we want a 95% confidence interval, we would find point, or inside of our normal table, this is 95%. So the area remaining on the outside, these portions, is 5%. So we have to split that up into both portions. So this is really 2.5%. And this is also 2.5%. So we could go to our table, table A in the back of the book, and we can say and find the z that corresponds to 0.025. And if we go to the back of the book, get your book and check that out in the back of the book, we would have z equal to negative 1.96 would be this z right here, and this z would be 1.96. So we call this our critical value, which I believe is what we're going to talk about on the next page, and we actually use z with a little star beside it to show that. We can also use the calculator. Remember, we can do inverse normal, where we go to second distribution, I think it is, and find it that way. So you can either use the table or the calculator to find our critical value. So we don't make the critical value plus or a negative. We just find what it is. We're going to find it in the book typically as a negative, but we just use the positive value. So the critical value for 95% confidence level is 1.96. So use table A to find the critical value, Z star, for an 80% confidence interval. Assume that the large counts condition is met. So an 80% confidence interval means that 80% or 0.8 is in the middle of our normal curve. So we have this area is 0.8. which means there's 20% remaining. So this side has to be 10% and this side has to be 10%. So we go in the back of our book and to table A and we look for 0.1. What Z corresponds to 0.1. And when we go and look for that, and here's a sample table, when we go look for that, 0.1, it looks like it's closest to negative 1.28 right here. Whoops, yes, right there. So the closest entry is Z equals negative 1.28, which means that our Z star, our critical value for an 80% confidence interval, is 1.28. (96% confident). Use table A to find the critical value Z star for a 96% confidence interval. Assume that the large counts condition is met. So the first thing I'm going to do, because we want to show this on the AP test, so I'm going to draw my normal curve and I'm going to put 0.96 here. So that means I'm trying to find Z and negative Z star where I have 4% remaining, which means I'm looking for 0.2 here and 0.2 here. So I go into the back of my book and I look for where is 0.2, sorry, in the back of my book. Whoops, not 0.2, that's 20%, 0.02. So I go in the back of the book and I find that Z is equal to negative 2.05. So my critical value, Z star, is just 2.05. Hope that makes sense. If you have questions, jot that down. We have a few more things to go over. Once we find the critical value, our confidence interval for the population proportion is P hat plus or minus the critical value times the standard error. So we get our Z star based upon whatever confidence interval we want to use. So suppose we took an SRS of beads from the container. We got 107 red beads and 144 white beads. Calculate and interpret a 90% confidence interval for the proportion of red beads in the container. Your teacher claims 50% of the beads are red. Use your interval to comment on this claim. So our sample proportion was 107 out of 251, which was 0.426. We checked the conditions earlier in this chapter. So now because we want a 90% confidence interval, that leaves us 10% left. So we want each side of the normal curve to have 5%. So we're looking for 0.05. And if you look at our table in the back, you can see that Z is going to be between these two exactly, between negative 1.64 and negative 1.65. So we're going to use a 90% confidence level, a critical value of 1.645. So now to find our confidence interval, we take our P hat, which was 0.426, we plus and minus that to the critical value times the standard error, which the standard error is P hat times Q hat divided by N, the square root of that. So once we add and subtract those, we get an interval of 0.375 to 0.477. So this tells us we are 90% confident that the interval from 0.375 to 0.477 captures the true proportion of red beads in the container. Since this interval gives a range of plausible values for P, and since 0.5 is not contained in the interval, we have reason to doubt the claim. So our teacher told us that there were 50% of the beads were red, but you can tell from our confidence interval 50% is not in our range. So we're thinking, teacher's probably wrong. That's not true. So here we go. We're now going to construct our own confidence interval. So Mrs. Quinn's class took an SRS of 102 pennies and discovered that 57 pennies were more than 10 years old. Calculate and interpret a 99% confidence interval for P, the true proportion of pennies from the collection that are more than 10 years old. And B, is it plausible that exactly 60% of all the pennies in the collection are more than 10 years old? Okay, so first thing, we already checked previously that we're okay to do this. It was random, it passed the 10% rule, the large counts was okay. So first thing I'm going to do is I'm going to find my P hat. Oh my goodness. Okay, now I'm going to find my P hat, which we did before, was 57 out of 102. So our Q hat was 45 out of 102. We need to find the standard error, which is equal to the square root of P hat times Q hat divided by N, which was 102. So I got a standard error of 0.049. Okay, so next thing we have a 99% confidence interval. So we have to find Z star that corresponds to that. We can use our table A, or we can use our calculator and do inverse normal. But if we go to our table, remember we have 1% left, so we have to split that into the two ends. That means we have 0.5%. So we're looking in our table for 0.005. The other thing we could do is we could do inverse normal on our calculator, and if we do that, we should write on our paper inverse normal. The area we're looking for is 0.005. Looks like a 3, but it's a 5. Our mu is 0, and our standard deviation is 1. So that gives us a critical value of 2.576. So I used my calculator to find that. So now to find the confidence interval, we take P hat, which is 57 out of 102, plus or minus the square, or 2.576, the critical value, times our standard error. So in my calculator, I'm taking 57 divided by 102 plus 2.576 times, I'm going to go up and grab that answer that we had before. And for my plus, I got 0.685. When I do subtraction, so that's one of my answers. When I do the subtraction, I get 0.432. So I'm going to say our interval is 0.432 to 0.685, and I'm going to say we are 99% confident. Remember, these are the words that we wrote the other day. We are 99% confident that the interval from 0.432 to 0.685 captures the true proportion of the pennies in the collection that are more than 10 years old. I'm out of room and it takes up too much space, so I'm not going to write that. But you need to write that every time. So letter B says, is it plausible that exactly 60% of the pennies in the collection are more than 10 years old? Well, since 60% falls within our interval, I'm going to say yes. So for part B, I'm going to say yes, it is plausible that exactly 60% are more than 10 years old. Probably should better in context, because 0.6 is in our interval. So there's my justification, or my explanation. Okay, so I hope that that made sense. We're kind of tying it all together today. Tomorrow we're going to focus on the four-step process that you're going to have to show every day, from basically from now on for everything that we're going to do. We're going to do this four-step process, and we'll figure out how we can find n as well when we're given other information. If you have questions, comments, concerns, jot them down, let me know.